Okay, now that we know a little bit about definite integrals, I'm going to show you some properties that can help you out with solving some of the problems. In all these properties, if you ever see an a, b, or a c, they are understood to be constants. And something I probably should have thrown in is that my functions f of x and g of x are integrable, meaning there's no crazy discontinuities or something funky. That's probably something you probably would have just assumed anyway, but I'm going to throw it in there to satisfy the Math League of America, although they're probably very upset with that absolutely horrendous writing, but whatever. All right, property number one, the area under a function f of x, if you go from a to a, that area will be 0. And if you think about that graphically, regardless of where your function is, if this is f of x, if I'm finding the area and I don't go anywhere, then all I've got right here is a infinitely small, if you want to think about a rectangle, there's absolutely no area to be measured right there. So if you don't go anywhere, the area would be 0. So there's property number one. Property number two, if you are doing the area under a constant, meaning your function that you're finding the area under is a function like y equals c. What am I doing here? Here's my pen. So this is like I have some function y equals c, and the area would be c times b minus a. Now, honestly, y'all probably would solve this without thinking about this property, but if you look at it graphically, if I have a function y equals c, that just means I have a horizontal line. So I'm going to graph a horizontal line at y equals c. It's going to look like this. If I'm going to find the area under that curve from a to b, let's say this is where a is, and this is where b is. Whoops. Okay. So I'm finding the area from a to b. Well, if you look at that area, all I've done is I've created a rectangle. And if you want to find the rectangle's area, you multiply base times height. Well, the height is c. The distance between a and b is simply going to be b minus a, and that's what this area is right here. It's c times b minus a, because all you're doing is finding the area of a rectangle at that point. Now, that said, if you forget that property, for example, if I have the area from 1 to 3 of the function 6 dx, if you forget the property, that's okay, because you could do antiderivatives. The antiderivative of 6 would be 6x, and we would evaluate that from 1 to 3, which will be 6 times 3, which is 18, minus 6 times 1, which ends up being 12. So you could also work out with antiderivatives if you happen to forget this property. So yeah, there we go. All right, let me see. I'm going to erase all this mess. Moving on. Property number 3. The area under a curve, if you have a constant times the function, you actually are allowed to grab that constant and move it outside the antiderivative, almost like you're factoring. And that's what I've done right here. I've just taken the constant, I've moved it out, as long as it is a constant times the entire function. If it's not times the entire function, then you cannot pull it out. Same thing down here with number 4, and same thing. They're not really related at all. Why did I say same thing? Okay, anyway, number 4. If you're finding the area under the sum of two functions, you can actually split that into two different antiderivatives. This is a property we're going to use quite a lot when we get into more advanced antiderivatives. But all we're going to do is find the area under f of x. Whoops, got to get that dx in there. The area under f of x, and then the area under g of x, and we work those as separate antiderivatives. You don't have to do that every time. Sometimes you'll just do the antiderivative, even if there is a bunch of addition and subtraction inside the integral. But sometimes the antiderivative technique for f of x will be completely different than what we do for g of x, and in those cases you'll have to split up your antiderivative. Let's see. Blank page. You know what that means? Triangle man, triangle man. Let's see. There we go. Now we get to take triangle man and throw them all over the place. Okay, good enough. Wasting time. All right, next integral, or next property. If you're doing the area under f of x, and you do a to b plus the area from b to c, those morph into the area from a to c. And the two things you have to look out for, you have to make sure that the function is the same. The function must be the exact same, and the upper limit of the first one must be the same as the lower limit of the second one. So those have to match up in order to use this property. And for this one, if you think graphically, which I'm a fan of thinking graphically, if we have some function f of x, and I just randomly choose some a, b, and c, so I'll put a right here, I'll put b right here, and I'll put c right here, and I find those areas. If I take the area from a to b, that's what this first antiderivative is saying. If I take that area and I add it to the area from b to c, then you are finding the entire area from a to c. Just make sure it's this exact same function inside both of the antiderivatives. And property number the last, and this one I'm not really going to draw anything to illustrate it, but the area from a to b of a function is negative the area from b to a. So if you flip the limits of integration, and we're going to do this a lot also, let's say I have the area from 1 to 3 of f of x, whatever the function is. I'm just about to rewrite the whole thing, but with numbers. If it helps you, and sometimes it will help you to flip the integral, then we can flip it from 3 to 1, but you have to make the integral negative. And I really don't know what that accomplished, but hey, it's there, so we're going to leave it. Let's see, so speaking of negatives, this does introduce negatives into antiderivatives. And so we have to think about how negatives show up in regards to area. And when I say negatives here, I don't mean bad things. I mean negatives is in the opposite of positives, which is still not a bad thing. Whatever. Right. So the one way you can get a negative area is if your function is below the x-axis. So let's say I have a function. Let's put my function down here. This is f of x. This area from a to b, I'll give you an a to b. Actually, I'm not even going to say a to b. I'm going to give you real numbers just for the sake of having real numbers. We haven't had real numbers much today. So let's say this is from, we'll say from 2 to 4. If I'm finding that area from 2 to 4, that area actually is going to end up being negative. So if I were to do the area from 2 to 4 under f of x, and I use the word under loosely because under actually means between the function and the x-axis, that will be a negative area. The reason it is a negative area goes back to the good old Riemann sums. Let's think about Riemann sums. Let's say I were to do this area with 2 rectangles. So I'll put a rectangle from 2 to 3 and another rectangle from 3 to 4. If we think about those rectangles, regardless of whether I use left endpoints or right endpoints, I'll draw left endpoints here just for the sake of choosing one. But if you look at these rectangles, the area of one of these rectangles, if I go from 2 to 3, my change in x is 1. I increased 1. If I go from 3 to 4, my change in x is a positive 1. However, the heights of these functions, what in the world? I missed that terribly. What is going on here? Ah, now I can't reach. Oh, wait, there we go. Left endpoints. There we go. All right, now if you look at the heights of these rectangles, my heights go down below the x-axis. So the height of this rectangle is whatever f of 2 is. And right there, f of 2, that y-coordinate is a negative number. So the heights of these rectangles is negative. So if I'm finding the area of these rectangles, I've got a positive base, but a negative height. And when you multiply positive times a negative, you get a negative area for that rectangle. So if you're going from right to left, and your function is below the x-axis, you're going to end up getting a negative area. Another way you can get a negative area is if your function is above the x-axis, but instead of going from left to right, as we typically do, if I went from right to left, we would have a negative area. So let's do kind of the same thing. We'll go from 2 to 4 again. I'm just arbitrarily picking numbers, so we'll call that 2, we'll call this 4. And if I were to draw rectangles here, let's say we're finding the area from 2 to, not 2 to 4, I'm finding the area from 4 to 2. Now that's kind of backwards because now we're starting at 4 and traveling left to 2. Well, this area again is going to be negative. And the reason this area is negative goes back to that rectangle concept when we're doing Riemann sums. And I'll choose left endpoints just for the sake of choosing something. So I'll do a left endpoint Riemann sum there, a left endpoint Riemann sum here, except now my change in x, if I'm going from 4 to 2, and I'm actually going left, my change in x, if I go from 4 and I end up at 3, my change in x is negative 1. If I go from 3 to 2, my change in x is negative 1. So we actually have a negative base for these problems, but the heights of these functions, these y-coordinates, are positive. Yeah, all of these y-coordinates for the heights are positive. So I have a positive height and a negative base. And when you multiply positive times a negative, you do get a negative area. So if you're going from right to left and your function's above the x-axis, then you have a negative area. And then the last example I wanted to do here, how much time have I spent? 10 minutes. Not too bad. Okay, what if you're finding area from right to left and the function is below the x-axis? So now we're kind of combining the two, and y'all are pretty astute. I bet you know what's going to happen here. If I'm going from right to left, and my function's below the x-axis, so we're going to stick with the good old 2 to 4, and I'm traveling from right to left, so I'm going to do the area from 4 to 2 under this function. Okay, this time, well, let's see. If I split this up into two rectangles, I'll put 3 right here, and if I draw my rectangles and we think about what's happening here using left endpoints, well, if I go from right to left, this time the base and the height are both negative. 4 to 3, my change in x, my base is negative 1. From 3 to 2, my change in x is negative 1. So I have negative changes, negative bases, and my y-coordinates for my heights are also negative. So in this case, I have a negative times a negative for the base and the height. I actually end up getting a positive area in that case. So there are ways to get negative areas, and it depends on the direction you're traveling and the position of the function. Not to be confused with position, velocity, and acceleration. Okay, so there's the basics of some properties of integrals. I have 3 problems with real numbers that I wanted to look at. Let's see. Number 1, area from 1 to 5 under a function is 12. Area from 4 to 5 under a function is 3.6. What would the area from 1 to 4 be? Now, in this problem, a lot of you probably could just look at it and say, well, 1 to 5 is 12, 4 to 5 is 3.6, so we're going to subtract the 2, and that would be correct. But I'm going to kill this thing dead just to make sure that we're seeing how the properties work out. Let's see, the area from 1 to 5, the area from 1 to 5 of f of x is the exact same thing as the area from 1 to 4 under f of x plus the area from 4 to 5 under f of x. And if you look at what's given, the area from 1 to 5 was given. That's 12. Area from 1 to 4 is what we're looking for. And the area from 4 to 5 was also given. And now we just solve the equation, only the unknown is this big, huge, honking antiderivative. So I will subtract 3.6. Subtract 3.6 and get an answer of 8.4 for the area from 1 to 4. Yeah? So that's kind of how those properties are at play. Now some of y'all are thinking, well, why don't we just kind of sketch this out? Because this is the algebraic way of solving it that I just did. If you're a graphical thinker, then you may be thinking, okay, here's my x-axis, here's my y-axis, I have some function, f of x. I know that the overall area from 1 to 5 is going to be 12, and the small area from 4 to 5 is 3.6. Maybe I need to make a note that 12 is extending the whole way, and 3.6 is simply the area right there. So you could subtract the 2, and you can see graphically why subtracting 3.6 from 12 gives you the area from 1 to 4. Right. Okay, let's try another one. The area from 0 to 9 of a function is 37. 0 to 9 of a different function, g of x, is 16. Then the area of this would be what? And in this problem, we're going to do that little trick where I showed you could split up an antiderivative. So we're going to change this to the area from 0 to 9 under 2 f of x plus area from 0 to 9 under 3 g of x. And then I could go one step further. Remember, if you have a constant times the function, you can pull these constants out. So I'm going to pull the 2 out. I'm going to pull the 3 out. And that gives me 2 area from 0 to 9 under f of x. That's a goofy looking 9, isn't it? Plus 3 area from 0 to 9 under g of x. And the areas from 0 to 9 of each function were given. So that's 2 times f of x. The area under that is 37, plus 3 times the area under g, which is 16, which is what, 74 plus 48? This is dangerous. I'm going to do this in my head. 122. Woo, that's scary. I think I'm right. But remember, in AP Calculus, unless this is a multiple choice question, you don't have to simplify. So I would actually accept 2 times 37 plus 3 times 16. Yeah? Yeah, all right, last one. Area from 1 to 5 is 12. Area from 3 to 5 is 14. What's the area from 3 to 1? All right, let's see. I have 1 to 5 is given. That's going to be the whole thing, right? Maybe I'm going to solve this by graphing. I may do this one more in a graphical way. So let's see. I have some function f of x, area from 1 to 5. That whole area is 12. The area from 3 to 5, so I'll put 3 right here. That area from here to here is 14, right? That means in order for these two areas to add up to 12, this area right here must be, that area must be -2, because then -2 and 14 would add up to 12. So this is actually a bad graph the way I have it drawn, because a -2 area means I should be below the x-axis, because the area from 1 to 3 is -2. However, I want the area from 3 to 1. So looking at this graph, I can tell that the area from 1 to 3 under my function is -2. That means the area from 3 to 1 under my function is +2. Yeah. So there we go. That's the graph way to do it. If you wanted to set it up more algebraically, you could. Let me just do it in thinking land over here. You could say, and this is, by the way, this is going to be bad math. I'm about to write some stuff that would make the Math League of America cringe, and I'm doing this just for the sake of time. I do have the overall area from 1 to 5, right? So the area from 1 to 5 would be equal to the area from 1 to 3 plus the area from 3 to 5. And that's using that property where if you're doing areas, the area from 1 to 3 plus 3 to 5 is the area from 1 to 5. Well, the area from 1 to 5 was given. That's 12 equals the area from 1 to 3 plus the area from 3 to 5, which is given, is 14. Then if I subtract 14, I get -2 to be the area from 1 to 3 under my function, which means the area from 3 to 1, which is what I asked for, under my function would have to be +2. So there's a couple of different ways you could do that. You could set it up graphically, which I'm perfectly okay if you want to sketch the graph and work it that way, or you could set it up more algebraically. It's purely up to you.